So in this video, we're going to look at the simple harmonic oscillator, and that's just what we call the most fundamental type of oscillator. And so the easiest example of this is a mass on a spring. So we're going to prove later that this actually is simple harmonic motion, but really once you've done that, this mass spring system is the easiest way to think of what a simple harmonic oscillator really is. So that's what we're going to start using, and what we're going to say is that we're going to see the kind of the types, the characteristics of this motion, and we're going to say those are the kind of the key things for all types of simple harmonic oscillators. So we're just going to assume right now that this is a simple harmonic oscillator, but we will prove it later. So we start with this mass in a spring, which we're just going to say is at x equals 0, where this is our equilibrium point. It's our point of zero extension of the spring, zero displacement. And then we're going to, this is obviously our spring, sorry, and then this is our mass. And then we're going to pull this spring and then release it, and what happens? So we're going to move it to x equals a, which is now going to be our amplitude, and x is our displacement, which in this case is the extension of the spring. So x is displacement. And so what happens? We pull it to x equals a, and then we release it. What we see is that it moves back towards its equilibrium point at x equals 0, but then it keeps going because it's still got velocity. It hasn't slowed to a stop by the time it gets to x equals 0. In fact, we're going to see later that's its maximum speed. So then it keeps going. It goes all the way to x equals minus a, where eventually it's stopped and v equals 0. But then it just comes back on itself towards equilibrium. So we can see this would be x equals minus a back here, because we've stopped there and then we keep going back again. We've still got velocity v, and again it's exactly the same as when we came back this way. We get to x equals 0, but we've still got velocity, so we keep going. And then it slows down to reach a stop at the point we released it, which is back at x equals a, before repeating the steps above. So now we're here with v equals 0, but we're at this extension, so we're going to start accelerating back towards x equals 0, and then keep going again, and we're just going to repeat this over and over. And so we're going to oscillate forever actually without something to slow us down. So what do we see from this? Well, the main thing is that we're always slowing down as it moves past equilibrium. So its magnitude as the magnitude of its displacement increases, the magnitude of its velocity decreases. So what does this mean? Well, we're going to put up here exactly what it means. So basically, I think what happens to v as we're going from x equals a to x equals 0, and then as we go from x equals 0 to x equals minus a, and then x equals minus a to x equals 0, and then x equals 0 to x equals a. So what do we see? Well, first of all, what's the sign of v in all of these things? We must have that, again, taking the sign, x is positive in this direction and negative in this direction. We must have that v is negative when we're moving from x equals a to x equals 0, because we're moving back on ourselves. We're moving from positive x to smaller x. So v is positive, v is negative here.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.